Why does most of what you hear about AI agents feel like complete hype? They are promised to run entire companies, but they often fail at simple tasks. In our last video, we covered the basic difference between a chatbot and an agent. But today, we are going deep under the hood of agent architecture. We will dissect the core brain, the memory stack, the tools, the planning, and the reasoning systems. By the end, you will understand how these pieces execute real world workflows. If you want to master these advanced systems, subscribe and like the video. Let's crack open the engine. Cracking open the engine reveals that any autonomous agent is built on exactly four core pillars. First is the LLM brain, the central coordinator. Second is the memory stack, which acts as the agent's database. Third is the planning engine, decomposing goals into subtasks. And fourth is the tool belt, connecting the agent to the outside world. Together, these four systems turn a stateless language model into a complete dynamic cognitive engine. Now, let's look inside each system, starting with the processor itself. Let's start with the foundation, the LLM itself. This is the brain of every agent. The LLM receives three inputs simultaneously: a system prompt, the user's goal, and the context history. But the context window is strictly finite. As history grows, old information is pushed out and forgotten. And worse, the LLM is stateless. Every query starts from a complete clean slate. This is why we must build memory systems outside the model itself. So how does an agent actually remember anything? It uses three distinct layers of memory. First, short-term memory. This is the rolling context window we just saw. It's fast but limited and temporary. Second, working memory, the agent's personal scratchpad. Here, the agent distills conversation logs into core summaries, parameters, and extracted facts, pinning them so they are never lost. And third, long-term memory. This utilizes a high-performance vector database. The agent converts rich context files into high-dimensional numerical embeddings, storing them permanently. When needed, it runs a similarity check, like a highly advanced librarian searching a massive library, and pulls relevant histories back into the context window instantly. Memory lets an agent remember, but tools are what let it actually act on the real world. Here's the key. The LLM never actually executes tools. It doesn't run Python code itself, and it doesn't browse Google. Instead, it decides which tool to call based on context. When a tool is needed, the LLM generates a structured JSON object. This specifies the tool name and target parameters, like calling Google search with a specific query. The surrounding system intercepts this JSON, physically executes the tool in the real world, and retrieves the results. Finally, these results are injected back into the LLM's context window. The agent now has real-time data to solve your task. Without planning, an agent is just reacting blindly. Planning turns an agent into a systematic problem solver. When given a complex goal, like plan a trip to Kathmandu, the agent first performs task decomposition. It breaks the huge task into clean subgoals, search flights, check hotels, and outline the itinerary. But the real world is full of surprises. What if a flight is sold out? A simple rigid script would crash here. A true agent uses dynamic replanning. When it hits a dead end, it dynamically prunes that failed path, pivots, and generates alternative dates and hotels to bypass the roadblock. This high adaptability is what makes agents feel genuinely intelligent. They navigate uncertainty to actually get the job done. Building an agent starts with the system prompt. We instruct the model to write its thinking step by step before selecting an action. Next, we define our tools as standard code functions. The language model reads the doc strings to understand what arguments to pass. A simple Python loop drives the process. It repeatedly feeds the current state to the model, parses the action, runs the tool, and appends the observation back into the history. In action, the loop executes. The agent thinks, triggers the web search tool, and receives a metro population of 1.5 million. But our evaluator checks the result against the prompt. Catching the metro proper mismatch, it reflects, loops back to refine the query, and successfully retrieves the city proper count of 1 million. I am leaving this episode with a question. Do answer down below in the comment section. If an agent can plan, execute, and critique itself, when does it stop being a tool and start becoming a collaborator? Subscribe to follow this cognitive revolution step by step. Next time, we look at tool calling, how agents actually interact with our world.